looking back at this week, one aspect that was really impressive is the enormous range of topics that were covered by the talks. And moreover, there were talks more on the mathematics side, very hard to understand for chemists and physics like myself. And I presume the reverse is also true. The talks on the chemistry or physics side, 1 hour talking about essentially ill-defined objects, and then drawing definite conclusions must be, I imagine, difficult for the more mathematically oriented people. So what should the goal of the discussion that we are now having, what should the goal be? And I would suggest 2 things. So one thing is just to ask questions. So have let's say the chemists and physicists, do we have questions that we would love to be answered by the mathematicians, things that we just don't know how to handle ourselves, and maybe we could use some inspiration from the mathematics side. So that's one thing. And the other thing is maybe to identify something like a grand challenge or a few grand challenges that our community should envisage. So I have earlier today, knowing that I would be the chairman of this last discussion, asked a few chemistry and physics colleagues of mine if they have questions that we would love to know the answer from the more mathematically oriented people. And a few people have indeed expressed some questions of this kind. And yeah, maybe we, since Arthur was the last speaker, maybe we just directly continue with your question that you posed, and then we see how it evolves.
Okay. Yeah. Fine. Thank you, Hardy. So yeah, the question that we were dealing with in the context of non-adiabatic dynamics near conical intersection is that some of the functions, well, electronic functions, they have a double valued character, and this is not something that we deal on a regular basis with. So with these functions, when we use them as a basis to solve, say, differential equations, or to even like differentiate them and operate with these objects, like do the calculus operations, I felt a little bit uneasy that yeah, well, we may we may not know the proper calculus even to do some operations properly, and that's why I posed like a general question: is there a simple way to understand the operations with double valued objects? And we're trying to essentially come up with a work around those problems, but I was wondering, is there like maybe more straightforward ways to deal with the double valuedness in a mathematically correct way?
Actually, if I may, there is a calculus of multivalues functions developed for optimization problems. And I can give the name of this calculus in a second. I just have to look it up. I just have to look it up later. I read it in one of the books, about it.
Is that Kleinert book? There is this book on multivalued calculus.
Mm-hmm.
written by a physicist, but
Okay.
I read it in Russian book, so like
Yeah, I had a suspicion that in the differential geometry, people deal with manifolds all the time, and it's just I guess I never had the time to really go through it because there are big books and you need to go from the beginning to, and that's closer to the end, and then they discuss this question. So in the sense that this I don't think it's a very fundamental question that I'm posing. It's probably already, well, people know how to deal with these things. I was just wondering whether there's an expert in audience that could maybe give a simple intuition how that's like, there's nothing complicated. You just do this, and then the problem will be easily solved or addressed. So I was hoping for that quick
no,
fix.
my understanding is that these are topological quantities. Topology is exactly where calculus no longer works. And there is no alternative calculus. There is only calculus. Now, you can find workarounds by working formally. And, for example, this book, Multivalued Fields is the name. These things, of course, appear in superfluids. They appear everywhere in physics, but they are always an outstanding problem because there is no calculus. There are workarounds sometimes, but there is no systematic way like the one you are, in my understanding, you are trying to invoke.
Okay.
Okay. Yeah, that's an important message to know. Yes. I want to pose also a question that vaguely related. That was posed by Basile. He's in a plane now, so he's not able to pose it himself. It has also to do with the Born-Huang expansion. Ultimately, one forgets about continuum states, right? So one has the Born-Oppenheimer problem with fixed nuclear positions, and usually there's continuum states of the molecule. Is that important?
Well, I think it could be quite important, because if you study processes which say electron
ionization,
ionization is going on, then, but for others it could be quite unimportant.
Mm-hmm.
Can you explain a little better what you are referring to? Like continuous states, like what do you mean?
So not scattering states, so not eigenstates in the mathematical sense, but so not L2 functions,
Okay.
scattering states. Yeah.
So there is, if I may, there is a formula called Sigurd states, where you sort of rotate K to the complex plane, and then the scattered state sort of becomes like eigenstates. So this things, there is a work in actually old work from 2010s trying to use this approach in for strong field ionization, actually some simulations. And the good advantage that it's sort of like this biological continuation becomes sort of like a normal states. They become discrete. I mean, normal is of course they're never normal, but at least they're discrete. So perhaps that will allow to keep the summation finite at least. I can probably shoot an example of a reference which that is of interest.
So the Sigurd state, I thought that what you're describing sounds a lot like resonance states.
Yeah.
Referring to that.
It's just specific kind of definition of the way you construct these states. Yeah.
But with these resonance states, I guess they are not the there are states like that, but they don't form the yet complete spectrum of states. Like there are still states which are neither resonance but still in the continuum, I guess. That was my understanding, that the resonance states are not not all states that are in the continuum. They could be just some states.
I mean, if you, I will show the reference. It's a good paper. I mean, it explains the states very well. Like it defines them. So I would not like to comment more. It was a while since I read this.
Okay, now that would be useful to have. Yes. Mhm.
That's maybe a related question, kind of tangentially related.
Yes.
So, would anyone know a good reference to look for the following? Namely, what is if there's a mathematically rigorous treatment of how the sort of update formula for the quantum state reads when you have basically this continuum states. So if I make, usually the formula that I'm familiar is that if I make a measurement and I obtain a result which is an eigenvalue of an observable, so it's like a properly like diagonalizable observable that I have an eigenvalue that I measure, then there is this formula that to update the density matrix, which involves dividing in the denominator by normalization, which is something like the trace of the density matrix conjugated with the spectral projection onto the eigenspace of that eigenvalue. But if the measurement is for some type of continuum observable, like, I don't know, position or something like that, where it's strictly not an eigenvalue. I mean, it's in part of the continuum spectrum of the operator, and so that denominator would kind of like formally vanish. So there must be some type of I don't know, some kind of limiting procedure or some other approach that would modify that the standard formula. And I haven't been able to find a treatment in the literature, so I was wondering if anyone might know a good place to look. Maybe you need to use a rigged Hilbert space or some other construction like that.
So one reference that comes to mind is the people that deal with discretization of wave functions, because they have to deal with this transition. And I think the paper is by Littlejohn in the Journal of Chemical Physics. And I can find the paper and send it in. Yeah. So they have to deal with this transition from a continuum variable to a discrete variable, and it might be the thing that you need.
Oh, okay.
That actually reminds me, this problem that you're describing, it's even worse because, like, when you teach to undergrads quantum mechanics, you say, well, there's this collapse of the wave function, and well, like, what are you going to collapse if you have if you're measuring position, you're supposed to collapse on a delta function. Oh, but
Exactly, yeah.
now it's not L square integrable. So, like, how are you going to collapse on something that is not even physical? So the whole thing collapses. And I think, like, just to keep yourself kind of sane, for me, what was useful is to look at the von Neumann kind of explanation of what happens during the measurement, this decoherence process. And I think the going through that process, if you just analyze what's going to happen when you do this decoherence, it's probably going to decohere to some wave packet. Instead of being delta function, it's just some wave packet. And then the details will depend on the measuring apparatus, really.
Mhm.
But this decoherent argument that all you need is just the exponent of the Hamiltonian of the system times the momentum of the pointer for device, that kind of helps you to understand how the decoherence helps and happens, and then there is only a choice part that somehow happens. I don't think that part is understood completely these days.
I think maybe I would confirm that, because for the description of called atom measurements, if you do atom wave interferometry in the most advanced setups, you would actually say that you measure projectively the density of the atoms. So if you have a matter wave you measure it at a position, then you're actually counting whether you caught some atoms into a box. And that actually regularizes the whole problem very nicely, because the density behaves nicely, and then you integrate it over a box. And the wave packet decoherence comes about actually from the point spread function, because you measure actually the absorption of the illuminating light, and that then the photons diffuse in the gas, and this gives rise to the Gaussian envelope that you then assign to the density. So basically, it's really how the experiments measure it, that the pixels on the CCD camera correspond to the central points of Gaussian wave packets, and the yeah, and the spread of the wave packet is the pixel size.
Do you have a reference on this?
Sorry about my internet, I think.
Yeah, Marek, would you have a reference on what you just said?
Yes, actually, this is based on work by Yuri van Nieuwkerk, Fabian Essler, and Jörg Schmidtmeyer. And they really carefully worked it out, because for the new experiments, it's becoming always more important, because then you have the capabilities of using some RF pulses to outcouple atoms, and I think the experiment is slowly getting into a regime where you can make maybe weak measurements onto the system. I think that's where Jörg wants to be headed with the system. I will send the reference, but this is basically where a paper that has taught the community around the experiment what is actually being measured. So everybody was quite happy about this. But the main lesson was that if you look at the density of the atoms at the position, then it's a very nice observable, and it's physical, because you can do it. I mean, the density has a nice spectrum bounded from below, so it's nicer to make sense of that operator. And the way it works is that the free particle Green's function during the expansion is encoding the momentum distribution onto the density. Then that's the main idea. So I will send the link in a second.
Okay, cool. Ignacio, you also had a question.
So my question, I will try to approach. I was trying to connect with this meeting, so I'll pose a question that I have had for many years, in which I cannot reconcile quantum classical dynamics with fully quantum dynamics. So I can see why numerically they agree in the observables on why they mimic correctly, but I have conceptual difficulties trying to think about processes such as entanglement, but in a mixed quantum classical setting, where you just have a bunch of energies that have some dispersion that evolve differently between members of the ensemble. And I was wondering if there is a nice way to connect these two.
Can you maybe clarify a little bit, like what would be the simplest example where we can think about your question?
So the simplest example will be, for example, in your photoexcited dynamics, you could have a wave packet moving in that potentially surface. And if you think about it quantum mechanically, what you're having is that your electrons are entangling with your nuclei. But if you think about it from a quantum classical perspective, what you have is a swarm of trajectories. You're only describing the electronic part. You're not describing the nuclei. And the nuclei are introducing a dispersion in the energy levels of the electrons. And those energies will have some dynamics. And then when you look at electronic observables, you see that the two things sort of coincide, no? But in one case, you have a swarm of quantum classical trajectories, and in the other case, you have entanglement between electrons and nuclei. And I just don't understand very well how to put these two things together.
And also, when you say quantum classical, you probably mean like it would make sense probably consider not Ehrenfest and surface Hopf in some ad hoc ways, but rather something more rigorous like Capral's ways, like quantum classical Liouvillean type of approaches, where it's like it's more systematic in a sense. I think.
That's true. He has this unraveling, no, of the Liouville dynamics and into these stochastic trajectories. And I was just thinking Ehrenfest or
okay.
noise-induced decoherence or something simple. Yeah.
If we think something simple, I'm afraid the answer I would say, well, it's quite simple. Like you do some ad hoc approximation, and then if you did ad hoc approximation, then there is no hope to connect two things because it's like you did some approximation essentially, which is not which essentially breaks down the connection in a sense. It's like you're just switching in one formalism to something, and that is not paralleled by another formalism. So like if you can systematically go, like example could be in the Feynman formalism with the path integrals. If you systematically go from quantum to classical, then it's one story. Then you can see how things emerge or disappear. But if you just do the abrupt change with removing some terms or removing some elements from consideration, then I would say it's hopeless in a sense.
That's good.
Okay. I don't know, it's just ad hoc methods. Or maybe what is done with exact factorization could address some of this. So I guess with the exact factorization, it's a question to Hardy. The transfer from the fully quantum to quantum classical, is it in some sense systematic, or can it be made systematic, or it's always going to be ad hoc?
If you really mean classical, fully classical treatment of the nuclei, then I think it's
ad hoc.
It's ad hoc. I mean, it's in a way that's the point I always try to make. It's a way of identifying uniquely what the classical force is, what the force on the classical nuclei is when the nuclear wave packet splits.
Mm-hmm.
Right? And there's indeed a unique answer up to within gauge transformation. And that's a bit surprising. There's no choices there. But so you have this unique nuclear equation for the nuclear factor, and you just take the classical limit, right? So you know what the forces are, and that aspect is that's a nice aspect of it, I would say. But then still, it's classical, so you lose certain things for sure. Right?
Now I'm wondering, can this address the choice problem in the measurement?
I was wondering, yeah.
Because there as well, it's like a decoherence where, but the device produces a certain result anyway. So somehow it chooses between the two options.
So if you think of decoherence that is produced by the nuclei on the electronic subsystem, right? Then if you look at the electronic equation of motion of the factorization, you can identify one term that actually creates or induces decoherence. And so this is what I mentioned in my talk, this non-Hermitian operator, which nevertheless leads to a norm-conserving dynamics.
Mm.
Now, so we see this. If we drop this term, then you don't have decoherence. If we include the term in simple models and other situations, we can really take it or not take it, and then we see this. If the term is present, so the way and decoherence is always kind of a basis dependent concept. So we look at the electronic density matrix, the off-diagonal elements in the Born-Oppenheimer basis, and then see as a function of time how they go to zero. And if you do Ehrenfest dynamics, for example, or surface hopping, they don't go to zero, they just stay constant. So it is this term. And what I have in the back of my mind is that this, since it's one term, one operator, complicated object, but it is this thing that you can identify, this may be a way of actually controlling decoherence. Right? You may influence with an external field this operator in a particular way so that you prevent decoherence, or you make the decoherence time longer. This is exactly what you want in quantum computing. So this would be a dream to achieve, right?
Hardy, on that topic, recently we discovered that when you have not only pure dephasing contributions to the decoherence, but you also have conical intersections in the sense that you have space-varying diabatic couplings. What you find is that the decoherence dynamics depends on the initial phase that you create in your initial superposition state, no? And that is now a path for laser control of electronic decoherence. So I wonder if at the end those conditions will also be reflected in this term that you're referring to in the exact factorization.
I would expect that, yes, definitely, yeah. Yeah, this is one aspect to influence or control decoherence by choosing the initial state, but you may have additional fields. Yeah.
So in that context, we also developed like a two laser control scheme to control the decoherence that is based on impulsive photoexcitation, in which a first laser creates a superposition and the second laser generates interference, and you can control actually the decoherence dynamics. I wonder if by looking then at this quantity that you're referring, this scheme can be extended to more general photoexcitation schemes. I would be very interested in seeing this.
Yeah, that's exactly what I mean. Yeah. Okay, that is a cool project. Yeah.
That is a great project.
Yeah. So you worked on this two laser decoherence control.
Yeah, it was very interesting. So we discovered that we could control the decoherence by just changing the phase of the initial state for an initially separable state, and then we worked on how to create those states with lasers, no? And then we discovered that we only get this if we start with initially separable states, but if you start with a real eigenstate, you lose it, no? and
Interesting.
So that made us realize that it was an artifice of the initially separable states, even when the fidelities were great, like 99.9%. But based on those insights, we discovered that we could really create an initial electronic superposition state, no, with a given phase, with a given laser, and then use another laser to generate an interference and then control the electronic decoherence dynamics. So it seems very closely related to what you're referring to.
But I would imagine then the potential energies on which this wave packet are moving, they should be somehow like in some sort of special, because if decoherence is just related to decay of overlap, I would imagine lasers shouldn't help because the overlap decays and that's it, you kind of lost the coherence. If I'm thinking about like one like a wave packet of one electronic state is on the sloped surface and another is like in the minimum, so you create the kind of overlapping wave packets on two states, and then naturally they decohere because one moves away, another stays, and nothing would reintroduce the coherence in that case.
You're exactly right.
Okay, but somehow you are thinking about setup where that doesn't happen. It's like some sort of special wave.
So let's see. You can, using this setup, you can actually make the decoherence faster or slower. But I think the problem that you're mentioning, that once you create an initial superposition state and that initial superposition state evolves to a very different part of conformational space, it's gone. That's when you're not controllable anymore. So whatever you do, it has to be at the beginning when you still have some electronic coherences between the two states. Yeah, and in that context, is controllable. Yeah.
I see. Okay, so this is for molecular systems or some?
Well, if models are molecules, yes, for molecules.
Well, I mean, even in this case where you so to say lose part of the wave packet, if you think of a laser that then you have Floquet surfaces, right? You change the surfaces in this way.
Oh, you need to have strong lasers then.
And then you need strong lasers, but okay, you can create with a strong laser situation where this part that wanted to move away actually comes back. So that's conceivable.
Yeah, that's also another problem that we're working on, of using laser-induced potentials to control the decoherence dynamics, and that is also tractable. Yeah. I mean, we have never used. I mean, I think that the new idea here is using the exact factorization. I think it will just be fascinating to see whether from the exact factorization you can get general criteria for the control. Yeah. Because the criteria that we have is based on an early time expansion of the decoherence dynamics. This is what we use. But it looks that what you're talking about, Hardy, is general. It could lead to longer time decay and things like this.
Yes, yes.
And it could be implemented directly into the Floquet, no?
Yeah, yeah. Now I remember your paper where you look at the initial quadratic behavior, right? To get the decoherence time. Yes. Okay, I thought you have a more longer.
So we do dynamics, no? I mean, this is the starting point, and then we do quantum dynamics, and then we look at this. I was not going to talk about that tomorrow, but I could. No, I was going to talk about. I was trying to interface with this meeting, so I was going to talk about mixed quantum classical and quantum descriptions of the decoherence. Yeah.
Okay. Other questions? I have one kind of grand challenge. So we haven't really talked much about solids. So if you just think on short time scales, you let's say you just have electrons, nuclei are fixed. Then kind of, if you think of a relaxation process after a strong excitation in a metal, let's say, you get something like thermalization. So the electrons thermalize among themselves. So they are, in a sense, their own bath. Can we treat this somehow with the things that have been discussed in this week? So, I mean, here mostly we were talking about a system and a bath, and often thinking of a molecule in a solvent. So the bath is kind of classical oscillators, and we have a system bath coupling. So that's the typical situation. But with the electrons that thermalize among themselves, That's kind of different. So how would one treat this in a proper way? So this is and there's more and more experiments coming up on this type of systems. You also can create new phases. That's another issue by laser excitation.
Hardy,
But-
can I add to that question? I mean, I agree with everything that you
Yeah,
said,
yeah.
but I just want to add: are electrons interactions can they generate electronic decoherence? Because since I cannot distinguish electrons, if I call my system electrons, I never understood why electron scattering can induce electronic decoherence. I can see why, if I look at currents, it can lead to a current decay. No.
Mhm.
Yeah, okay, that's the question.
Yeah, exactly. Yeah, that's part of it. Yeah. So I would love to know how to deal with that.
Can I make a comment? I will not answer the post question, but I'll make a comment. That there is in a solid state, there is an interesting case of strongly correlated systems where sort of the electron interaction dominates. And what they're interesting is that it's, for example, it's well described by Fermi-Hubbard model, a very simple model of solids, of electrons interactions. And what's interesting about it is that if you were to take this problem and treat using band theory, according to the band theory, these materials are supposed to be metals. But because of a strong electron interaction, they actually become insulators. So they're called special name, the Mott insulators. And I just like Professor Grossi just said this, and it kind of makes sense. It's just like as if there's its own decoherence happening. Like it seems like I don't know. I'm gonna Google. Maybe somebody reinterpret this in this way. It's a well-known kind of classical. Means by classical means sort of like traditional high-end condensed matter physics, strongly correlated systems. And the model is so actually complicated, even though it's very trivial model, like mathematically. It's so computationally challenging that, for example, solving in 2D on lattice is basically, it's like, it's people are still struggling with it, and like, probably.
Oh, sure.
Yeah,
No, I'm very familiar with that. So I'm basically a solid state physicist. So that's I know very well.
So what would you say? Is it somehow related to what you're asking? Could it be related?
No, not really. So it's, and I'm not sure if are you talking about a thermalization in a Hubbard model?
I'm just talking like simply phase diagrams.
Just the Hubbard model itself. Yeah.
Indeed.
No, that's a different question. So what that I'm familiar with, and there one within these models has a pretty good understanding of this particular type of strongly correlated systems, that is Mott insulators. Yes, no, that's one thing. But once you have a strongly driven system, right? So you really hit a solid, can be any solid basically, right? If you hit it strong enough, you have a distribution of the electrons that is non-thermal. It's something weird after the strong excitation, and this can even be measured. And after a while, 50 femtoseconds or so, you have a thermal distribution, just the electrons among each other. They thermalize among each other. How can you describe this?
Oh, this actually, I bet no, because we published a paper, and not only us, it's basically people use a precisely Hubbard model to describe like strong high harmonic generation in a strongly correlated systems. And what they see, for example, even if you take a metal, right, because you can take a metallic phase. Metallic is what happens if you apply a short pulse. It's really short pulse, right? So there's no time for nucleus to move, nothing. Like it's it's femtosecond dynamics. There's no way.
Exactly.
For bosonic degrees of freedom play any role. And what happens, you see that the spectra response, optical response, is continuum. It's actually coherent continuum light. And the reason is that because within this half cycle of the laser pulse, you actually induce a transition from a metal to insulator, to a Mott insulator. and the Mott insulator gives you this like a white light, coherent white light. So it is describable by both by Fermi-Hubbard models coupled to laser fields very well. This precisely this dynamics. There's a string of papers actually about this right now. As you correctly said, some kind of.
I would have expected the opposite. If you start with a Mott insulator, right, and then you create electrons, hot electrons in the other bands, then you have a metal. So it's actually the other way. I would have expected the other way around.
It's the other way. Yeah, it's exactly. Yeah. So my PhD advisor, Misha Ivanov, published like a Nature Photonics paper a couple of years ago about this. So he was the first one to report on this. He was not the first one to work on it, but he was the first one to publish it. Yes, it's yeah. So it's exactly this is I find this effects extremely fascinating. Also, we also recently kind of motivated by precisely this field of research. My postdoc, who is not here, we are collaborating with Alexandra Lanzmann. She's also a strong field physicist. We were looking at metal, 2D metal, simple model 2D metal, 2D. And it turns out, if you start actually coupling, if you play with the couplings between, basically coupling between hopping parameters in one direction, the other direction, you actually can start seeing an emergence of an insulator in one direction. It behaves like an insulator, as if like electron repulsions like kick in, as if but they're not really there. So it's so I would just mention that basically all these effects could be described by lattice model, like by a simple classical lattice models.
Okay.
At least qualitative.
Hardy, I wonder if what the problem that you're mentioning, do they know if the thermalization, you see it both at the many body level and at the single particle level, or do you only see it at the single particle level?
I would, so theoretically, I would guess you see it only on the many body level.
Okay.
And you need electron scattering to thermalize.
Absolutely, but they're looking at the Fermi-Dirac distribution for the single particle states or for the many body states.
So well, they what they calculate from the many body wave function, the momentum distribution, right? So okay. That, I mean, it's calculated from but it's single particle observable, right? It's just the probability of finding an electron with momentum k.
Yes. Okay.
And that's also what is measured, right? So if you hit the solid with a laser, and then the electrons come out, and you can measure the distribution function.
But I'm wondering this many body level that probably is there, but in the case, if we just ignore it for a moment and look at almost free particle quasi momentum there, right? So it's almost like a free particle situation with the bands. Those bands, they have different energies, and if it's a coherent superposition of different bands, wouldn't this also create decoherence, because it's like physically similar to having a wave packet in a free space, which essentially dephases, right? So some components move faster, some components move slower. So you don't need a target on which it scatters. It's like just will fall by itself. But maybe the physics that you are talking about is that would not be satisfactory for that to describe that physics, because this flow in motion is just too slow compared to what they observe. It's like what they observe is faster than that, and that's why we need the many body effects to describe this.
What you described, would you expect that this leads to a thermal distribution?
Right. So that would not lead to thermal distribution.
So there is a distinction between decoherence and thermalization, I guess.
Right. Yeah, and that what you're describing also sounds similar to the process that they have in like a plasmon oscillations. because plasmon oscillations, they are somewhat harmonic, but they are harmonic for the Hamiltonian that is, well, it's like has harmonic terms, but that's not the full Hamiltonian. And as I understand that these plasmonic oscillations will not persist forever. It's like they will create electron hole pairs and yeah, decohere eventually.
Yep.
Right. So yeah. Can you give a reference on this like works that you mentioned for the metals?
Yeah, I can look for that. Yes. Mm-hmm.
And Hadi, what about the MFT? What do you think about those approaches where people actually try to quantitatively match up with ARPAs and so on?
Yeah, no, for the static situation, this is a very good thing, right? I mean, it neglects the longer range correlations that is known, but often you can describe things like a standard Mott insulator extremely well with dynamical mean field theory, definitely.
But out of equilibrium, it sort of also works, no?
There's some work there. I have my doubts.
Because if you do pump probe techniques, I mean, you can try to match up with those relaxation timescales, no?
Yeah, I know that this is what some people have been trying. Yes. Yeah.
But you're not satisfied with this yet, or?
Mm. I mean, this yeah, it's very specific idea of keeping mainly the local correlations, right?
Yeah.
Once you have a strong excitation, is that actually still the right picture? I mean, you have a soup of electrons in the valence in the conduction band, so it's somehow I have the feeling I cannot really prove it with a good mathematical argument.
Yeah.
Well, somehow is the wrong picture once you have strongly excited the system.
So in my PhD, I was working on closed system equilibration, but it's really hard to prove anything there, and
Right.
in
So
the end,
those are real systems, not model systems, like with the full molecular Hamiltonian kind of.
no. So we were working on generic quadratic Hamiltonians, for example. And then the hope is that by some sort of quantum Kam argument, it still holds out of equilibrium, and then you can also try to verify this with tensor networks. And then for those kind of systems that we would focus on, you can always try to do some optical lattice experiments, some of which have been done, but it's something that people are trying to do to verify some relaxation timescales there.
You said quadratic Hamiltonians, but I would assume that like those are not Hamiltonians where you can write coherent states and they will persist forever. It's like harmonic oscillator type of.
Yeah, so we were also focusing on counter examples. So we have fairly good characterization of what kind of conditions are sufficient for thermalization. And the way it works is that basically you show relaxation of local observables, so the system can really act as its own buff. And the nice thing is that you have a very simple model where you can prove everything from start to the end, and the only approximations are in the assumptions in a way, right? So you choose quadratic models, you take initial states with exponentially decaying correlations, you assume a finite range of the hopping, for example, and then you can prove it. And for example, if you're on a lattice and you have a finite range, then you already have a finite bandwidth, and if you have and then you can show that that short wavelength excitations will relax actually. So then, for example, the correlation length is allowing you to exclude some long range correlations, and the finite bandwidth gives you the curvature that makes all the wave packets spread. So how do you were saying, for example, if you excite the system, then you will have a complete mess, some excitations running through the system. But if you could prove some quasi-particle decay processes, then those wave packets would actually scramble, and they would form a shifted baseline for the thermal excitations.
That's conceivable, yeah, sure.
So,
yeah.
But how to prove it, nobody knows. I mean, there was a Fields medal for showing random dumping, so you know.
Right.
Can I ask maybe a little bit more mathematical question? In some of these considerations, at least another area I'm interested in is quantum computing and simplicity or complexity of Hamiltonians. And so what you're describing, I'm just wondering, can you formulate some sort of algebraic criteria? It's like my Hamiltonian can be represented as certain operators, and those operators form Lie algebra or some sort of there is some closure relation between the operators that are involved. And then we know harmonic case, for example, is like that. And fermionic case is also like the excitations form the algebra. And that makes it like easy to formulate certain states, like coherent states that will just persist and they will just and the dynamics will be easy. But have you thought about that more algebraic approach to your problem?
Yeah, I mean, so the way it works, we have just quadratic Hamiltonians as generators in the works that I was involved in. And then basically what we characterize is the behavior of the single particle Green's function, and intuitively what we prove for those Hamiltonians. So when we consider classes of models, we are targeting a certain property of the Green's function. So the Green's function initially it's a delta peak, and then
but let me stop here. Like when you say quadratic, let's say there are two simple examples which are very different. Spin Hamiltonians, if they are quadratic, not necessarily exactly solvable. Fermionic quadratic, always exactly solvable. So quadratic doesn't really guarantee.
Yeah, sorry. I meant like quasi-free models in the sense of quadratic forms for bosons or fermions. And
Okay.
but then basically the idea is that you go to the Heisenberg picture and use the single particle Green's function to basically smear those operators. And then you use linearity and you have to control the different contributions. But what we found is that you can do it with quite big generality, and it really has a large resemblance to a central limit theorem. Because, for example, if you look at the second moments and you expand it, you have basically a large polynomial which is quadratic. And then what the Green's function can give you is basically this suppression that you have in a central limit theorem. So in a central limit theorem, you have a 1 over square root n normalization of your random variable, right? And if you have diffusion in the single particle Green's function, it's 1 over square root t. So basically the volume of the light cone is giving you this suppression. So the time in which you spread. So you can spread ballistically, but if you have a finite bandwidth, then you have the stationary phase for the wavefront, which is t to 1/3. So this one is slow. So basically it's additional 20 pages to control that one. But the bulk of the system is going t to -1/2, and this is basically the CLT. So basically you can get a small parameter, which is the system size. As soon as the excitations move through this whole system size and you have some sort of diffusion, then basically the wave packet is becoming homogeneous and flat. And then you have incoherent contributions. And So if you don't have long range correlations, everything is factorizing, and then everything becomes sort of trivial, so you can control it. So what we were learning from those single particle models is really that the system size is giving you the small parameter, and to have the system size in play, you have to have some sort of transport, or at least that's a notion of some sort of ergodicity for those single particle models, that the wave packet spreads everywhere it can, right? So I'm constrained to the single particle space, but inside of this single particle space, I can move fairly homogeneously over the volume. So that was one of the papers that we wrote, where we were using some techniques from analytic number theory to make some bounds that you could also do in principle with stationary phase. But we sort of entered a little bit into to some off topic, but there was a paper in parallel where people did the same thing with stationary phase. And what we were really learning there is that we couldn't make headway for any interacting models because there was no bounds on transport. So that there's no good notion for transport in the interacting case, or no practical way of phrasing it such that it's provable, and so that was becoming tough. There are works, and that's again maybe coming back to Hadi's question. There are works on the return to thermal equilibrium where it was possible to make rigorous bounds, but they are not quantitative in time. So it's really the time estimates are really unpractical, and that's sort of the open question in this kind of corner of mathematical physics, how to make those times practical.
Somewhat related, but somewhat different as well. Topic that I was involved recently was okay. You mentioned quadratic Hamiltonians. Those, if you think about eigenstates of that systems, they like factorizable usually, or it's like I would call it even mean field solvable. Meaning that if you use sort of mean field procedure, it's usually will give you an eigenstate exactly. But the question we were looking at is like, okay, what is the most general form of the Hamiltonian that allows factorizable eigenstates, sort of beyond quadratic? And can in like in electronic structure, can we have 2 electron or 3 electron or 5 electron Hamiltonians, like many body Hamiltonians, which will have eigenstates which are still like a Slater determinant, for example, right? And yeah, things like that. So it turns out that there is a way to construct such objects. And interestingly, what we found is that there are some Hamiltonians for which it's essentially you rotate like orbitals, molecular orbitals, and you will obtain only one eigenstate out of many. And in order to obtain another state, you need to rotate the orbitals in a different way. You won't essentially, with one rotation, obtain all eigenstates, but there are rotations that will give you other states. So I don't know whether anyone has interest in that, but kind of useful to know which Hamiltonians can be treated with the simple methods, essentially.
But were the Hamiltonians that you constructed somehow local, or
when you say local, I have some understanding what you mean, but would you mind kind of giving the definition what you mean by
like
local?
maybe in space? So if I think of a band model, if I want to have a Gaussian ground state.
No, it's like we are operating in second quantization. In there, well, locality is usually like 1 electron, 2 electron Hamiltonians, essentially in the powers of A and A dagger operators, bosonic or fermionic. We mostly work with fermionic operators, and locality is corresponding to number of the degree of the polynomial that you are making. So 2 local would be 1 electron Hamiltonians, 4 local would be two electron Hamiltonians and so on. So in that sense,
But the spatial dependence of the terms that you needed?
No special dependence, because then in the second quantization you kind of working in the potentially delocalized orbitals.
Yeah, but
One particle basis can be localized or delocalized.
Yeah,
right.
the thing is that I always thought that you have quasi-free ground states or eigenstates only if you have all-to-all couplings for the higher order terms. So that you cannot select them to act only on part of the modes.
Okay. Well, when you are dealing with indistinguishable particles, usually you do have kind of all the orbitals involved in this second quantized form. It's not like one is connected only with 2 and 2 is only to 3. So like there are no limitations. The usual limitation goes like there is like 1 electron terms, 2 electron terms, and so on. But all orbitals or one particle states are involved.
Yeah, it's just yeah, I'm not so familiar with the more chemistry way of phrasing.
No, it's like a many body physics. It's like if you have a second quantized form, it could be bands, for example, in the solids, it's like one particle, like A dagger A.
Yeah, so I can give you one construction for such Hamiltonians. Basically, you could consider an Anderson model on a line. So A dagger A, the hopping, and then disordering the local chemical potential on a line. So if you go to the eigenmodes, they are exponentially localized in space, right?
Okay.
So now I could take the occupation number of any of those localized Anderson modes and take the quartic or higher order mode and add it to the Anderson model.
That's right. Yeah,
but they are simultaneously diagonalizable. And but the problem is that you don't have the interplay of ballistic transport versus a local potential, and that's what you have in the Hubbard model, because you already have a disordered quadratic term, and you're adding this local potential, but already it's localized versus localized, so you don't have this competition of a localized potential versus something that has momentum like eigenstates.
Sure, but we're coming from a different side. Essentially, in physics, we're dealing with Hamiltonians, which of course are not mean field solvable. They are complicated. But it's for some procedures in quantum computing, for example, it's useful to partition the Hamiltonian you're dealing with into something that is easily solvable parts, right? So Hubbard Hamiltonian in that sense will be easily, like there will be 2 parts. The hopping terms, they are exactly solvable, and the localized terms are exactly solvable. And so there is no way to combine those two and have a kind of mean field solvable Hamiltonian. But what you said is exactly one of the intuitions, is that if you have mean field rotations, unitary operators, and in between you can have either one single like linear combination of occupation or quadratic form of occupation operators or cubic and so on. You can have as many occupation operators as you want. When you transform them with mean field rotations, they will transform into some Hamiltonian, which will be complicated looking, but in reality it will be a very simple one that has eigenstates that are product states. So and there is algebraic kind of reasoning behind. It's like if you go to Lie algebras, every Lie algebra has actually so-called Cartan subalgebra, which is the largest subalgebra containing fully commuting terms. And occupation numbers is this Cartan subalgebra essentially. They are largest subset of elements that are fully commuting. And what you want to do is you want to put the unitary transformations kind of on each side and put in the middle everything that is commuting, and that's how you build the simple eigenstate Hamiltonians. Okay, yeah. And then you can decompose any operator in such fragments. And turns out, like in electronic structure, it turns out that this thing was people came to it from the slightly different kind of angle. It's this hyper contraction theories in electronics, like in the correlation methods, where essentially you try to decompose the Hamiltonian again into something that with like almost a generalization of SVD decompositions. Yeah. Right. But what wasn't interesting that the description I just gave, that occupation number in the middle and some mean field on the side, like on each side, that's only one type where one unitary transformation will rotate everything into the occupation number kind of representation. But there are types where one rotation is not enough to obtain all eigenstates, and that's something that like we haven't thought. But again, in electronic structure theory, people, when they do say transformations to simplify the Hamiltonian, like couple cluster theory so-called, then they can actually construct the transformation that can only obtain ground eigenstate. In the rest, the Hamiltonian is not going to be diagonal in that representation. It's only separating one eigenstate from the rest. And in a sense, the transformation makes the Hamiltonian block diagonal with one state, ground state, say, separated from the rest of the spectrum. And that's kind of analog that in some cases you need different unitary transformations, state-specific kind of unitary transformations to obtain different eigenstates.
Also, one example could be the Kitaev honeycomb model. Have you thought about that one?
Yeah, I heard that name, but no, I didn't look.
So it's a higher order model. It's not quadratic in the fermionic operators. And the way it works is that at each hexagonal placket, you have basically a flux of, it behaves a little bit like a flux operator. And those are constructed in such a way that they commute and become sort of quantum numbers. So once you fix the fluxes, by recognizing that they can be factored out, you have basically different levels of quadratic Hamiltonians. So each configuration of the fluxes gives rise to a different quadratic Hamiltonian. And Kitaev used this to come up with the phase diagram of that one, and then you get non-abelian anions as well, thanks to those fluxes coupled to the fermions.
Okay, I'll take a closer look. Yeah,
it's a wonderful paper. It's very readable. It's 120 pages, but it's because he has laid the foundations for category theory for classifying topological orders, but the first 10-20 pages, I think it's just 10 pages where he treats the model, and the rest is his appendix, his sort of notes. So yeah, so the 10 page, the first pages where he solves the model, it's really a really well written paper, and very instructive in a way. So it's really fun to read it, because it's also a great example for such a construction, I think, maybe.
Okay. And the main motivation is for different phases in solid state, or like what?
Yeah, so it's an explicit construction where you can really see what kind of excitations you have and what's the phase diagram, because it has an exact solution which is simple. And then he had those non-abelian anions, and then the idea is that those are the kind of anions that allow you for universal quantum computation as well. And people are searching for this also in solid state in quantum magnets, because there are those, I think it's called clock Hamiltonians or something like this. And then if you hybridize the orbitals in a special way, you can try to go towards the Kitaev model. And the fun thing is that if you go to a particular point of the phase diagram, you have the Kitaev spin liquid. So people are trying to find a spin liquid via this Kitaev realization, because they have a model where it's clear that it's a spin liquid. So it's this model is really rich. I mean, it's a really rich paper, and it's really fun to read. So yeah.
Okay, well, thank you. I'll take a look.
Okay,
All right.
it's almost 1 o'clock in Germany. So, okay, so maybe that's a good point to stop. Thank you for the discussion, it was great.
Yep, thank you.
Hardy.
Okay, and see you tomorrow.
See you.
Bye bye.